What we've done so far is that we have looked at simple regression models with a single predictor, not even a predictor, it was an intercept that we were looking at. This was the button pressing data, and I showed you how you can assume a log normal likelihood function to model how this data might have been generated. So now what we're going to do is we're going to build on that very simple statistical model and keep adding more and more structure to it. That's basically what the rest of this course is all about. So as an example, I want to think about a particular situation where we are doing a psychological experiment, and what we are asking the participant to do is to track between 0 and 5 objects on the screen as they move around, and then they have to what they have to tell us at the end of the trial is which of the items were there on the screen that we'd ask them to keep track of as targets, right? So to give you an idea of what this looks like graphically, so at the beginning of the trial, a subject will see a fixation cross, then they will see a bunch of points on the screen, and then some of the points will be distinctive in the sense that they're the ones that the participant has to track, and then these points start moving around on the screen, and at the end of the trial, the subject is asked to select the targets, the points that they were asked to track, right? So this is the basic issue that we are studying here, and actually the issue that one is studying, the cognitive process that one is studying, is attentional load, right? So how accurate are you at keeping track of the targets as attentional load increases? And load is increased by increasing the number of dots on the screen, right? So the question, the research question that we want to answer here is how attentional load affects pupil size. So we are recording the size of the pupil as you're forced to pay more and more attention to the task. We know that from research in psychology, we know that if you overload a participant and make them concentrate more on a particular task, their pupil size will increase, right? So it's called arousal, and so this attentional increase is something that you can model with this kind of experiment design, right? Okay, so what is a good statistical model for this? We can start simple, right? So let's start with a very simple model where we assume a normal likelihood, and the dependent variable here is the pupil size that we are looking at, right? N refers to the nth row in the data frame, right? So we will always be working with data frames, and the data frames will be indexed with the position in the row, which I'm going to call small n. Okay, so small n goes from 1 to capital N. Capital N is the total number of data points in that data frame, right? So the model that we are going to think about is pupil size is coming from a normal distribution with some mean and some standard deviation. So this you have seen before, of course, but what's new is that we are going to have a predictor in the mean component of the normal distribution specification here. So instead of just having a mu here, as you have seen before, we have an intercept as well as something that we call a slope, the beta parameter, which is going to be determined by the load that the experiment forces the participant to experience, right? So let's take a look at what will happen now when we fit such a model. Notice a very important assumption I'm making here, which is often glossed over, but this is an extremely important assumption. The assumption is that every data point in those n data frames is independent from every other data point. So in the frequentist world, we would say that we have independent and identically distributed data. Now, whether this assumption is actually satisfied or not in these data is a separate question. We are starting with a simple model, so let's proceed with this simple assumption, and then we'll elaborate on this model later on. Okay. All right, so let's first ask ourselves, what kind of prior specifications can we give to the parameters of interest in this model? What are the parameters? We have the alpha parameter, the beta parameter, and the sigma parameter. These are the 3 parameters in this model, very simple model, but we do need to define priors on these parameters. So how do we decide on what the priors are? Let's first think about the intercept, okay? With the intercept, I need to have some knowledge about what pupil sizes can be. Well, pupil size can't be negative, right? Whatever the units are, We don't know what the units are here, but there's some positive number, right? Pupil size cannot be negative. But we can do better than just speculating about this. We can look up some pilot data. There's lots of data out there on the internet, and you may have done some pilot research before you actually do the experiment. So you can examine some pilot data, and what I'm doing here is I'm looking at the distribution, the summary statistics on pupil sizes, right? So I see that, well, the minimum is 852 units and the maximum is 868, whatever this unit is, right? So this suggests something to me. And what does it suggest? It suggests that I could use a prior that would look like what's in equation 2. I could, for the intercept parameter, I could choose a normal distribution prior with mean 1000 and a standard deviation of 500, right? So what are we expressing when we specify such a prior? We are actually saying something. We are expressing a belief about what we think are plausible values of this parameter, right? And so how do I quantify that belief, right? You can do that with the QNOM function. That's why all these DPQR family of functions are so useful. So you can just take the QNOM function and pull out the 95% interval, that covers 95% of the area under the curve. And this tells you what your prior belief, before seeing any new data, is for the average effect, of pupil size. Right? That's what this parameter is going to represent, the average effect of pupil size. And this prior is now representing a reasonable range. I don't know, maybe this is too liberal, right? One could change this prior to something more informative, but we can think about those situations later, right? Now, for sigma, we could start by using an uninformative prior. As I have explained earlier, the posterior is going to be a compromise between the prior specification and the likelihood. And so if you have a very vague prior on the parameter, you will tend to get the same posterior distribution as you would if you were looking at the maximum likelihood estimate, right? So you'd get the mean of the posterior would be very close to the maximum likelihood estimate for a vague prior, right? So that was a demonstration I made a long time back in a previous lecture. So now, what we're going to do is, for the sigma parameter, because sigma cannot be negative, we're going to truncate the normal distribution at 0. So we're going to stipulate that you cannot get a value less than 0. So what we have is a truncated prior distribution. That's what I've got here. Normal distribution, mean 0, standard deviation 1000, truncated at 0. Okay, so you can plot this now with dnorm or something to see what it looks like. But you can also extract, using this extra dist package, you can extract the 95% quantiles, of this distribution. And you see that the range is pretty reasonable. It's quite liberal, actually. It's going from 31 to 2241, which allows for a lot of variability. So, but as I said, this is an uninformative prior, and we can work with this, and nothing bad is going to happen, if we use such an uninformative prior. Now, the last parameter of interest, which is the most important one, is the beta parameter. This is the parameter that represents the effect of attentional load on pupil size. And so I start with this kind of ballpark assumption about a beta parameter coming from a normal distribution. This is a prior now, with mean 0 and standard deviation 100. What this expresses is that the attentional load can either increase or decrease pupil size. Of course, this is not realistic. I mean, we know from research in psychology that if you increase attentional load, there will be a tendency to increase the pupil size will increase. But we want to remain agnostic. We want to leave open the possibility that you could go in the opposite direction. As attentional load increases, pupil size could, in principle, decrease. So that's what this uninformative prior is expressing. And you can quantify the 95% credible interval again as before, which expresses your prior belief about what plausible effects you could expect for increasing attentional load by 1 unit, for example, right? Okay, so what do the data look like? Well, what I'm going to do is I'm going to show you this DF pupil data. This is in the BCoxI package, which comes with the textbook. And so the first thing I'm going to do before we look at the data is to center the predictor. This centering is a very important thing that we are always going to do, or almost always going to do, when we do regression modeling, right? It has important properties. The details I cannot discuss here because it's pretty involved technically, but in the textbook we unpack this idea of centering in a lot of detail. So it's an optional extra you can look at if you're interested. But what we now do is, what does centering mean? Centering means that I take the vector of the different loads The different loads are the number of dots people are going to see on the screen, right? These are discrete numbers. So what I do is I take the mean of that vector, right? That's the mean of that vector, and subtract it from the load vector. What that does is it transforms the vector of loads, which are all positive values, 2, 4, 6, 8, and so on, into either negative or positive values. The values will be negative just in case the load is less than the mean load in the entire experiment, and they'll be positive if they're larger, right? And they'll be 0, of course, if it's exactly the same value as the mean of the vector load vector, right? So centering is a very useful thing to do for various reasons. As I said, this has to do with regression modeling. Not just Bayesian, but just frequentist as well. So I won't really discuss that detail too much here, but all I'm doing is I'm just showing you how you would create this vector called centered load. And this is the vector that I will use when doing the modeling, right? Okay, so let's just quickly take a look at this data frame before I move on. I've got a subject column, I've got a trial column, right? This tells me the trial ID, and notice that I have multiple measurements from the same subject. Subject 701 is giving me multiple data points. For example, load 0, I've got at least 2 data points from subject 701, right? So I have repeated measurements on this subject, even though I'm assuming in the toy model that I started with today that we have independent and identically distributed data. That's not the case, obviously, but let's start simple and then we can elaborate on this model later, right? Okay, so we have a predictor load which is centered, right? And now we're going to start to look at the effect of load, centered load, on pupil size. So let's see what happens, right? So the first thing we're going to do is to run the model through the BRM function. So if you've ever done any linear modeling, this first line should be familiar to you. We're just modeling pupil size as a function of an intercept, that's the alpha, right? And then a slope, centered load, right? And this is our data frame that I just created. Here I've defined the likelihood that I'm assuming, the normal likelihood that I defined, that's specified here. So generally you should always specify which likelihood you're using, just to be explicit. And the Gaussian is just a synonym for the normal likelihood, right? And finally, here's the prior specification. I've defined the priors I just showed you a few minutes ago. These are the priors that I just specified. Notice that for the sigma parameter, the BRM function, which is a front end for Stan, automatically knows that sigma has to be a truncated normal, right? If you specify a normal distribution here or some other distribution here, sigma will always be set to be positive because you cannot have a sigma less than 0, right? So that's something that's internally dealt with for you. This is good in a way because it's convenient for canned models, but it's important to know what the syntax is actually doing, right? So underlyingly, it's writing Stan code, and it's setting up the parameters and constraining them so that they have the appropriate range, okay? Okay, so we have just fit the model, and now in the next lecture, I'm going to show you what you can get out of this model. You're going to get the posterior distributions of the 3 parameters, and you can look at the posterior predictive distributions to see what you learn from this model and what the model predicts for future data, which is a very important use of statistical models in general, predicting the future.